In this problem, we have a lens combination, and we have an object sitting 25 centimeters in front of the first lens, which is a diverging lens with a focal length of negative 15 centimeters. Next, we have a converging lens with a focal length of 17 centimeters, and that's 20 centimeters from the diverging lens. We're asked to draw a ray diagram, including all three principal rays at each step, to find the image. We're going to use the diagram to approximate the image distance relative to the second lens and the total magnification of the image. Finally, we're going to use the thin lens equation and magnification equation to find the image distance and the magnification to three significant digits, and hopefully these answers compare favorably. So we start by getting principal rays through the first lens. A ray coming in parallel to the principal axis will be refracted away from the direction of the near side focus. Second, a ray coming through the center of the diverging lens is unrefracted. And third, a ray aiming toward the focus on the opposite side of the lens will be refracted parallel to the principal axis. So we have three diverging rays on the right side of this diverging lens, and we trace all those back to a common origin point. If you look through that single lens, this is where you would perceive the image to be, the common origin of the diverging rays. Two of these rays have already been traced back to the common origin point. There's only one left to do. Those line up pretty nicely, and that's where the image of the head of the arrow is going to form after the first lens. Next, we're going to run this image through the converging lens to find the final image formed by the combination. I start with a ray parallel to the principal axis, and that's going to be refracted through the focus of that converging lens. Then I can do a ray through the center of the converging lens. Finally, I take a ray through the near side focus of the converging lens, so that's the 17 centimeter focus right here, and that's going to be refracted parallel to the principal axis. Now when the rays come together at these shallow angles, it's pretty hard to be precise with the ray diagram, but somewhere around here my rays are converging to form my final image. Next, I'll get my approximate image distance and magnification, and the image distance here I mean relative to the second lens. So every two of these spaces is 5 centimeters, and I just count the spaces. And the final image is a little before the 40 centimeter mark. I'm going to call it 38 centimeters. And our approximate magnification can be found by comparing the height of the final image to the height of the original object. The final image, I'll say, is about 1.3 spaces. The original object was 3 spaces. There should be a minus sign on this because the final image is inverted. So that's about negative 0.43 for the magnification. Next, we want to check our approximations by using the thin lens equation and magnification equation to get a precise answer for the final position and magnification of the image. So to do this, we break it into 2 steps. We do the refraction through the first lens, and then we use the image from the first refraction as the object for the second refraction. And our toolkit here is the thin lens equation to find the image distance at each step, and the magnification equation to find the magnification at each step. Then we write down what we know at the first lens, and our object distance was 25 centimeters. Our focal length was negative 15 centimeters. So diverging lenses have negative focal length. And we want to find the image distance out of this. So I take 1 over f minus 1 over do. And this can be done in one step in a calculator, just negative 1/15 minus 1/25, 1 over that answer. And I get negative 9.38 centimeters approximately for that first image distance. Now these things should actually be indexed for our first refraction. And then when that image passes through the second lens, those will all have a subscript of 2. So our first magnification, I'll call that M1. That's a positive 9.38 over 25 since the image distance was negative. And I get a magnification of 0.375 at that first step. Then we go into lens 2, so we're just taking the image from the first lens. Remember that was an upright virtual image to the left of the diverging lens, and we're running that through the converging lens. So to get the object distance, I need the distance to the diverging lens added to the distance between the lenses, which was 20 centimeters. That's a total of 29.38. And the focal length of that converging lens was 17 centimeters. I solved the thin lens equation for 1 over di. That's going to be 1 over f minus 1 over do. And again, I can do it all at once in my calculator. and I get an image distance of 40.3 centimeters. That's to the right of the converging lens. My ray diagram approximation was 38 centimeters, so that's not too bad. My second magnification is negative di2 over do2, and I get negative 1.37 for this. Now the only thing left to do is to get the total magnification of the image. And the magnification at each step is just a scale factor for what percentage you change the height of the object by. So these magnifications simply multiply, and the total is given by M1, M2. First, we shrank it by multiplying by 0.375. And then we flipped it upside down and made it grow a little bit by multiplying by negative 1.37. The total effect of this is a magnification of negative 0.514. And our approximation from the ray diagram was about negative 0.43, so that's off by a bit. So we missed by about 15% in our ray diagram estimate, and the issue there is that the image was so tiny that our estimate of its final height had a huge uncertainty in it. If you find the physics content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce over 100 new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.